Hello, wonderful family of Metal Data. Welcome to another amazing session of our Python tutorial series. And as promised, in today's episode, we are looking at differentiation with symbolic mathematical Python, that's SymPy. And so if you haven't installed that already, you would want to do a pip install SymPy. And that should allow you get all the recipes and then the packages that come with the SymPy. Since I already have it installed, what we are going to do is just import SymPy as SP, and we are good to go. Just in passing, if you're new here, don't forget to subscribe and then join the bigger family. Let's learn and grow together. And so we import SymPy as SP, and then what we want to do is to now define the symbol. So for instance, we have X, which we are going to pass as sp.symbol. Then we pass in the X as a string. Now this would, when we run SL, this will produce X as a symbol. This is just as it would appear if we're using LaTeX, right? And so once we have that, what we do next is to define our function. So let's say we have y equals to 10x squared, or let's say 10x cubed plus 5x squared minus 15x plus 30. So there's our y, and we can print it out to see how it looks. And that's it. Now, when we're done, what we do next is, in order to perform the differential of this y, we just call our sp.diff and differentiate y with respect to, say, x. And we have the final answer. Okay. Now, if we want to evaluate this at a point or at a fixed value of x, what we want to do is we can pass this to, say, first derivative. Okay. And then we get to call the first derivative dot subs, which is to substitute, in this case, x with what value we are representing, x with, say, 3. And then we have the final answer. Okay. Now let's make use of a combination of trig functions and exponentials in C. So let's say we have a function, say, h equals to 35 sine squared of, say, x cubed. So we can print out the h to see what it is. And there's what it contains. So 35 sine squared x cubed. Let's say we want to add the exponential of, say, x squared, and that's it. Okay, so now that we have this function, we can perform the derivative, and so we will just call our sp.diff, which is to differentiate our h with respect to, say, x again, and then there's what we have as a derivative. As simple as that. Now we can pass this as, say, our fd, and then evaluate that. So we have, say, fd.subs, and then substitute in place of x, say we have 0.2. We get the final answer. Okay, as simple as that. And so that's how you make use of your differential or derivative function. Okay, so let's say we have this, just the sine function, and then we evaluate and we are getting this. Okay. Well, there are certain instances where, okay, yeah, that's it. So after performing the derivative, we still have the trigs showing. Yeah, the trig functions are still showing. And you want the final value. What we want to do is, in this case, you would want to import NumPy for what we are going to use. So we add in the importing part, we import NumPy as NP. And then we get to run over this. So let's assign this as a z to make it easier. So we have a z containing the output. Okay. So we want to run np.float on the z, and then we have a final answer. Okay, and that's it. Well, this produces a warning, which is telling us in some case, sometimes the company will be deprecated as np.float, but then currently it still works. And so this is it, and you get a final answer. And that's all for today's session. If you have any question, don't forget to leave them in the comment section and the team will address it. If you're new here, do well to subscribe, join the family, let's study and grow together. Do well to like the video and then share within your network. Until then, we'd like to say bye-bye and see you in our next tutorial video.